Okay, so let's talk about the mobile charge in an MOS system, the charge that carries the current in a MOSFET. In this lecture, we'll see how it varies with the surface potential of the semiconductor. So, current is proportional to charge times velocity, and the charge in the semiconductor is two types. The depletion charge, which we've seen before and discussed, and the mobile charge in the inversion layer, which we have not said a lot about. That's our focus in this lecture. The mobile charge in the semiconductor as a function of the surface potential. In the next lecture, we'll relate the mobile charge to the gate voltage. Okay, so first of all, we could think about the charge per unit volume. Mobile charge per cubic centimeter versus depth into the semiconductor. So the charge we're interested in, this P-type semiconductor we're looking at is going to be the heart of an N-channel MOSFET. So the mobile carriers are going to be electrons when we invert the surface and create a channel. So we're interested in electrons. Now, the electron density is going to vary as we move from the surface into the depth of the semiconductor. It's going to vary because it depends on the relative position of the Fermi level with respect to the bottom of the conduction band. And that is varying with position because we're bending the bands. You can see that there are going to be a lot more electrons near the surface because the conduction band has been bent down close to the Fermi level. Okay. Now, in the bulk, we have minority carrier electrons. Their concentration N sub B is Ni squared over Na. And so their concentration, the concentration of electrons will then increase as we move towards the surface, but it will increase because the bands are bent down, and it will increase exponentially with the potential. So at the surface, it will be e to the q surface potential over kT times Ni squared over Na. And that can be very much larger. When it becomes equal to the p-type doping density, we say we've inverted the semiconductor. But that charge is there below threshold and above threshold. It just continuously varies with surface potential. All right, now we're going to be more interested in MOSFETs in the integrated charge. Not just in the charge right at the surface, but the charge close to the surface. So we're going to ask, what is the charge per square centimeter when we take the total charge and charge density per cubic centimeter and integrate versus depth and get all of the charge that can contribute to the current. So the charge will be negative Q because there are electrons, and we'll integrate the electron density versus position from 0 at the surface of the semiconductor into the depth. Okay. So when we do that integral, we've seen that it's going to depend on the potential in the semiconductor. So I could change the variables of integration from position, y, to potential. I could introduce that by introducing a dy d psi and a d psi. I'm going to change the variables of integration. Well, how does that make things simpler? Well, I can recognize derivative of potential with respect to position is minus the electric field. So this term here that I've introduced is 1 over minus the electric field. Now, I'm integrating through a relatively thin layer of electrons. They're piling up near the surface. That's where most of the charge is. It's not unreasonable to pull the electric field out of the integral and say, I'll just assume it's constant at the value that it has at the surface. So if I pull it out of the integral, then we bring out the electric field at the surface. And now there's an integral that is actually easy to do. We can perform that integral, and then here's the result. The result is that the total charge of electrons per coulombs per cubic centimeter is minus Q times the concentration in the bulk, Ni squared over Na, times this exponential factor e to the q surface potential over kT. The units of these terms are per cubic centimeter. We are looking for a charge per square centimeter. So the other terms have the dimensions of length. kT over q versus surface electric field just comes from integrating this expression. How do we interpret that? We interpret that as the depth of the layer of electrons, the thickness of the inversion layer, for example. Okay, so we could write the total charge in the semiconductor as minus Q times the charge at the surface itself, which is what these first terms are, times the thickness of the inversion layer. All right, it's a good way to remember it. Okay, so we have a simple relation. This actually works pretty well if we do the calculation more rigorously. Simple relation between the total charge in the semiconductor as a function of surface potential. This is actually valid above and below threshold, because as soon as we start bending the bands, we get more electrons. There is a subthreshold current as well that we're going to be interested in computing. So we can use this above or below threshold. We have to be a little bit careful, and I'll discuss that in a minute. Well, let's look below threshold. So this would be the charge that we would need to evaluate the subthreshold current, the leakage current in a MOSFET. We have our expression for the charge as a function of surface potential. Now, we're subthreshold, so there are a few electrons near the surface that are carrying a small leakage current, but they're really not affecting the MOS electrostatics. We're still in a mostly depleted region. We can ignore those as far as the electrostatics is concerned. They carry all of the current, but we can ignore them as far as the electrostatics is concerned. So we can evaluate the surface electric field using our depletion approximation formulas that we developed earlier. So we have a simple expression for the electric field at the surface. Okay, so now it's a relatively simple matter then. We can evaluate this expression. We get an expression for the mobile charge as a function of surface potential. And the important point to remember is that the mobile charge increases exponentially with surface potential below threshold. Okay, so that's probably could have been expected, because we know that the carrier concentration depends exponentially on the separation between the conduction band and the Fermi level. Okay. All right, now let's go above threshold. So we'll begin with our same expression for the total charge. Above threshold, if we look at MOS electrostatics, it's a little bit different now, because we have to account for all of the charge. Above threshold, the charge in the semiconductor consists of the depletion charge and the inversion charge. It's the inversion charge now that we're interested in. Below threshold, the depletion charge dominated, so we could evaluate the electric field simply with depletion approximation results. But above threshold, the mobile charge dominates. Okay, so now we could say that we could apply Gauss's law again. We could say that the normal displacement field at the surface of the silicon is minus the charge in the silicon. The charge in the silicon now is all this inversion layer charge. So we're going to use this expression for the electric field above threshold instead of this expression below threshold. That'll be the difference. Now, there is one other thing that we need to be careful about, and that is that we are now integrating this carrier density versus position. There's a large number of carriers and a large amount of charge in a very thin region. We would expect the electric field to be very, very rapidly now. So it's not, when we had a depletion region, we could assume that the electric field was constant at its surface value. But now, when we have an inversion region, we have a lot of charge in a very thin layer. The electric field is actually going to vary rapidly in that layer. It's going to be approximately zero when we get below that layer, and it's the surface value at the beginning of that layer. So we'll just say, on average, when we're integrating through that layer, the electric field is half of its surface value. Okay, if that looks a little bit of a fudge for you, I'll point out that, you know, there is a more rigorous way to get these results exactly, and what we're trying to do is to get some feeling for why the answers come out the way that they do. But that is in effect the right numerical factor. All right, so now we have everything. If we use this expression for the electric field here, you'll see that we have a Q downstairs here. We have a Q upstairs on the left-hand side. That means we're going to get a Q squared. We'll have to take a square root, and the final expression will be this. If you look at that expression, the main thing you want to take away is that The charge above threshold also varies exponentially with surface potential, but now it's with Q times surface potential over 2 kT. And that 2 came in from the fact that the electric field is varying so rapidly as we go through the inversion layer. Okay, so now we can go back to this plot of charge in the semiconductor versus surface potential that we've been discussing many times. You know, we understand that charge piles up when we accumulate the semiconductor. We understand that charge occurs as we deplete the semiconductor and that it grows as a square root of the surface potential. But now we've looked at the mobile charge. The mobile charge is insignificant in this region, but it's there. And it increases exponentially with surface potential. The mobile charge dominates when we get well above the threshold voltage. And in that case, the mobile charge increases as surface potential over 2 kT. So we've been able now to explain quantitatively some of those features that I've been stating qualitatively in earlier lectures. So these are some important takeaways. Charge varies exponentially with surface potential, but there's a different numerical factor above and below threshold. So as I've mentioned, there is an exact solution for this whole problem. We don't have to do it separately below and above. We can do the whole thing exactly. If you want to see how that's done, it involves solving something called the Poisson-Boltzmann equation, and some notes that work this out completely are available at this particular website. Okay, so we have an understanding of how charge versus surface potential works in a bulk semiconductor. By bulk semiconductor, I mean one that is essentially infinitely thick. That is, everything that happens near the surface, the depletion and inversion, and then we have a neutral semiconductor that could go on infinitely long. That's what we call a bulk semiconductor. You know, 300 millimeter 12-inch wafers are 775 micrometers thick. That is really, really, really thick compared to the thickness of inversion and depletion regions. Okay, remember we worked out a depletion region example and it was on the order of 20 or 30 nanometers thick. Okay. Now there's a different class of devices that are more and more important in modern MOS structures. And these are transistors that use very thin layers of silicon that aren't even doped at all. So this, for example, is a silicon on insulator structure. It's known as an extremely thin silicon on insulator structure. And the heart of the device now is an MOS capacitor on a very thin layer of silicon that has no dopants in it at all, so there'll be no depletion charge. There is another realization of essentially the same thing. This is called a FinFET that you may have heard about. And these are transistors, you're seeing a cross-section here of a thin silicon fin. So this is like a channel that is rotated and vertical on a fin. A gate is wrapped around both sides of the fin. So it's like there's a gate on the top and the bottom, or in this orientation on the left and the right. This also is an nominally undoped piece of silicon that is fully depleted. So we should ask ourselves, what changes in these structures? We've understood the charge versus surface potential in a bulk semiconductor system. How does it change in the more modern systems that are in use in the latest technology? Well, we'll do a simple example that will really, help us understand both of these two structures. We'll take something that we call a fully depleted, ultra-thin body, double gate MOS capacitor. So there'll be a thin silicon layer, undoped, so it's fully depleted all of the time, we could say. A thin insulator layer on the top and the bottom, and a gate on the top and the bottom. And we'll try to understand as we apply gate voltages here and induce charge in this thin silicon layer, how do they respond to the potential. So when we talk about psi sub s now, it really won't be on the surface potential because the layer is so thin that there's just one potential. It's constant in the semiconductor. So psi sub s will now refer to the semiconductor potential. Okay, so we're going to draw energy band diagrams now in the normal direction as we've done before. If we do that, the energy band diagram would look something like this. we have a conduction band, we have a valence band, then we're going to have very wide band gap insulators on both sides of them. So what we have made is what people would call a quantum well. We've confined our electrons and our holes into a potential well. There will be discrete energy levels that we can calculate with particle in a box expressions if we have an infinitely high barrier. If we have a finite barrier, we have to be a little more careful, but the results are similar. We also have confined holes, so we have confined states there. So it's a little more complicated situation, but what happens is really not so different, we will see. So T sub Si will be the thickness of the silicon. It's not hundreds of micrometers as it is in a modern bulk wafer. It's now just a few nanometers thick. Okay. So one of the things you'll notice in here is that the lowest energy that an electron in the conduction band can have now is the first quantized energy level, E sub 1. The highest energy that a hole in the valence band can have is E sub 1H in the valence band. You can see that we've effectively increased the band gap of this structure a little bit as well. Okay, now if we ask what are the carrier densities in this system, I'm not going to go through the details, but you could integrate the density of states times the Fermi function over the energies in the conduction band, and you would get an expression that relates the carrier density per square centimeter, all of the electrons in this quantum well, to the location of the Fermi level. And the location of the Fermi level, what's important is how far above the bottom of the first subband the Fermi level is. If it's above the bottom of the second subband, we would have to add a contribution to the second subband. All right, so that's an expression. It's not so different from what we see in the 3D case. It's just that we are using now a two-dimensional effective density of states, which comes from the two-dimensional density of states of these confined carriers. Now, just as we've been doing for bulk semiconductors, we're going to assume non-degenerate conditions so that we don't have to deal with Fermi-Dirac integrals. We'll deal with Boltzmann statistics. And we would find, just as we found for the bulk material with three-dimensional electrons, that the electron density, now two-dimensional electrons, so density per square centimeter, varies exponentially with the separation between the Fermi level and the bottom of the lowest energy that the electrons can be at, which is the bottom of the conduction band plus epsilon sub 1, the energy of the first confined state. All right, so similar qualitatively to what happened in our bulk. Now, I'll point out that actually in the bulk, we do have a quantum well, and if we were more careful, we would consider those electrons in this quantum well as two-dimensional carriers and do the calculation that way. In fact, this is the first place in the 1960s when people began to observe the effects of quantum confinement in semiconductors. It was in these MOS structures. Okay. Now, in the bulk, this quantum well is due to the potential itself. In these fully depleted structures, the quantum well is due to the ultra-thin body, the ultra-thin layer of silicon itself. So in the bulk, the thickness of the quantum well changes with the bias, but for the ultra-thin body or FinFET example, the thickness of the quantum well is just the physical thickness and does not change as we change the bias. So now we can look at these energy band diagrams under different conditions. So we can begin where the surface in the semiconductor is 0. The location of the Fermi level will be somewhere, depending on the metal semiconductor work function difference, and we'll have some number of electrons and holes, hopefully small. If we apply a positive voltage to the gates on the top and the bottom, we'll pull all of the energies down, and we'll start to get more electrons in the quantum well. If we apply a negative voltage on both the top and the bottom gates, we'll pull the energies up. We'll get fewer electrons, but more holes. So we'll get energy band diagrams that look like this. Now, if we ask ourselves, what is the density of mobile electrons in this quantum well? It's going to be given by, it's going to depend exponentially on the separation between the Fermi level and the lowest energy in the conduction band that the electrons can be at. That lowest energy can move up and down as we change the potential of the semiconductor by changing the gate voltage. So we're going to find, not unexpectedly, that the sheet density of electrons in this structure will grow exponentially from its value when the potential was 0. It will just increase exponentially as e to the q psi s over kt. And the whole concentration will just do the opposite. It will increase exponentially for negative surface potentials. All right. So these equations assume that only one of these subbands is occupied. Things would just get a little more complicated if we had other subbands occupied because the Fermi level was above them. We would just have to add those contributions. So the net mobile charge is just the positive charge minus the negative charge. The only charges now are mobile holes and mobile electrons because we're assuming that this is an undoped layer. In practice, there will be some nominal, unavoidable doping density, even if we try to make the material pure, but it's small. So this is the dominant charge. So we conclude, if we're just interested in the mobile electron charge, that it's minus q times its value at 0 potential, which is determined by the metal semiconductor work function difference, times this exponential factor that involves the potential of the semiconductor. This is valid above and below threshold. We know there's no electric field involved in this calculation. So we can use it everywhere. So our charge versus surface potential would look very simple. It would just increase exponentially as we make a positive semiconductor potential, or increase exponentially as we make a negative semiconductor potential. Okay. Notice in these curves, there's no depletion charge on these curves. We only have mobile charge. So when we compare them to the previous calculations, we have the exponential characteristic in accumulation, we have the exponential characteristic in inversion, but we're missing the depletion charge. All right. Now, we've also noticed there is a different numerical factor. Above threshold, we had a factor of 2 in the denominator in the bulk case. That's because the width of the quantum well in the bulk case depends on the surface electric field. In the fully depleted ultra-thin body case, we don't have that factor of 2. So just to summarize, we have worked out the charge versus surface potential relation for a bulk semiconductor. We found that it goes exponentially with surface potential both below and above threshold. There's a numerical factor of 2 that comes in when we're above threshold. For the ultra-thin body case, we also find that the mobile charge varies exponentially with surface potential below and above threshold, but it always has a Q potential over 1 kT in the expression. All right, so that's a summary of how the mobile charge varies as a function of surface potential. Okay, we've completed what I wanted to cover in this lecture, but we know that we can't control the surface potential directly. What we can control is the voltage we apply to the gates. So in the next lecture, we will talk about how we relate this mobile charge to the voltage on the gate.